Hello everyone, today I'm presenting my work 3D to Smiles, translating physical molecular models into digital DeepSMILES notations using deep learning. This work is done by me, Wenqi Guo, Yang Du, and Muhammad Shahata. This work is done under University of British Columbia and Within Software. Previous educational research has shown that although virtual molecules models are as effective as physical models, students should have concrete models at least at the beginning of the stage of their study because humans sometimes rely on concrete objects. However, digital models have some learning curve, so it's not that easy for students to understand that in the early stages. And digital models do have some benefits, such as it's easier for them to look up some information using a digital model. And to the best of our knowledge, there is no available tools to convert between a photo of a 3D molecular models in physical space into the digital space. So this work is trying to bridge this gap. So this is our design use case. An app could be created, although not yet, when student build a molecule and then take a photo of it, our model should be able to translate that into smile string, by which is identical to each molecule and can be used to look up more information about the molecule. So our contribution in this project is that we constructed two datasets, one synthetic dataset and one real-world dataset. We train models on these two datasets and emphasize the importance of our synthetic dataset. We evaluate the performance with different dataset combinations, and if we use previous pre-trained models. And we also applied different techniques to the model to increase their performance, and we also analyze the model's properties using some methods. To the best of our knowledge, there is no tool to convert 3D molecular model images into their digital representation. However, there are some computer vision models that can translate a 2D molecular structure formula, such as this one, into smile string. Some of them targeted in handwritten molecules, some of them targeted into the printed or structure really clear, either printed by computer or hand drawn using a ruler, those things. And the Swing OCSR primarily focused on the printed molecule. DeepSMILES, they did both, and Campix mainly focused on the handwritten molecule. So using DeepSMILES, they first pre-trained the model on the printed molecule, and then they fine-tuned that on a strongly augmented version, so to simulate hand-drawn data. And using this spatial technique, they can increase the performance from 27% to 60%. So their process is a two-step process. They pre-train on the printed molecules, and then they fine-tune on hand-drawn images. So that's kind of similar to our work that I'm gonna introduce in the next slide, in the next few slides. So this is their model architecture. So they have an encoder. It's either EfficientNet V2 in DeepSMILES or Swing Transformer in Swing OCSR. And then they also have a transformer encoder right after the backbone, the image encoder. And then they have an autoregressive transformer decoder to decode it into a deep smile string. Autoregressive decoder is like GPT, is outputting a character, a token by token. Here is a character by a character. So it's not just outputting everything at once, it's coming out one by one. And our method require synthetic dataset. So to collect this synthetic dataset, we download the molecules from PubChem. We remove the 3D information because if we preserve the 3D information, here the oxygen might be in a weird shape and this carbon might have some behind another carbon or something. We have to find the right angle to render them. So to avoid this process, we remove the 3D information. So we flatten them on a 2D surface, but we still render them into a 3D space. We use Blender, a Blender script to render this thing in a 3D space. We collected about 80,000 molecules, and for each molecule, we collected about 4 images on different angles. So it's about 300,000 molecules in total. We follow the common CPK color schema, though this schema is used in the common molecular model set. And then we need the real data. So to collect the real data, we build a React.js mobile application with Supabase backend for volunteers to use. The screenshot of this application can be seen on the right side. Similar molecules will be grouped together by a GPT API. So basically, we give a batch of molecules to GPT and tell them to output the molecules and group similar molecules together. They collect the data on their own time, so some of them the data might not be really clean. There's some misbuilt molecules. There are some molecules that use the wrong color. So we build another application for another group of volunteers to clean the data. So at the end, we have 203 molecules and 1,933 images. This is about the first version. It's very limited. So we need to construct an algorithm, a model that will work with limited data. So these are some real data examples. So our algorithm is pre-training the model. So we adapt the swing OCSR model. We pre-train that on the synthetic dataset, and then we fine-tune that on our real dataset. Here we can see that without any pre-training, the token level accuracy can reach 60%. So we count the two molecule string. If each token match, we count as correct. So we have 60% of the character that are correctly matched. That's a decent result. However, when you consider the whole sequence as correct, the accuracy dropped to 0.38%. And if we use the swing OCSR pre-training, but we don't use our synthetic data pre-training, we get about 71% per token and 5.43% on sequence level. None of these are actually usable. And then we try to bring in the synthetic dataset. So if we use ImageNet pre-training for the encoder and swing OCSR pre-training for the decoder, and we then pre-train our model on the synthetic 80,000 dataset, we got 94% token level accuracy and 62.5% sequence level accuracy. This is a huge increase. And also, if we use the maximum potential of all the pre-trains, swing OCSR pre-training for both encoder and decoder, and synthetic dataset pre-training, we got 95.5% token level accuracy and 64.9% sequence level accuracy. This is a dramatic increase considering we only use synthetic dataset to pre-train the model. And here we can see these two are a same molecule in synthetic dataset and real dataset. They are really different, but our model can learn valuable information in the pre-training on the synthetic data. So we also try to use some techniques to improve our performance using bin search and multi-image input. So bin search is a strategy used to construct the output sequence. So like I said, the sequence is outputting token by token. However, for every time we outputting the next token, if we only choose the maximum property for next token, this is a greedy approach. It might not yield the best result. So a better way to do so is we maintain top K top sequence, and for each we go search all its children. So if here we can see for the bin, if we increase the bin from 1 to 3 and keep the image input as 1, we don't really see the increase in performance. And same thing for 2 images and 3 images. However, when the bin number is 1, we can increase the number of image input. This will slightly increase the accuracy. And if we consider the top end accuracy, so for bin search, the output will be the same number of answer will be the same as number of bins. So here, if we have 3 bins, you will get 3 answers. If one of these is correct, we count it as correct. This way, increase the number of bins will increase the accuracy because obviously you give it more trials. And increase the number of images, we still increase the accuracy. However, like on the left side, if we only increase the number of bins and consider the top one, the accuracy doesn't really increase. This is interesting. So then we examine the model's calibration. So here basically what we have is that for the top 3 answer, we can get one of them as correct. But the top one accuracy didn't increase. That means the model can output the correct answer within the top 3, but the model can't really decide which one is the best. So we and then examine the calibration of our model. A calibration of a model is the correlation between their accuracy and their confidence. Usually this is a measure of the expected error correction. However, here we can't really use that because our confidence is not ranged from 0 as 1. It is range from 0 to 1, but since it's the multiplied product of every token. So if the first token is 0.9, second token is 0.8, then we got 0.72, and when the sequence is very long, this value drop really quick. So we calculate the R2 square, the R square value of the best fit line. This is inspired that they usually use this in GCMS in chemistry. So we can see the R square here is only 0.25, which is not really high, and then we can see there is a trend in these dots, but they are not really while forming a line. So that means, yes, the model can output the correct answer, but they can't decide which one is the best. And we also examine the silencing map of our model. A silencing map is basically like where the model thinks the part of the image is important. We do this by taking a partial derivative of the image and the output token. So we can see here in the first step when the model is outputting a carbon, so just background information, all the black atoms here are carbon and the red one is oxygen. And carbon is C, oxygen is O, and the equal sign means double bond. And we can see here the first time when you output the token, we can see it is here on the carbon molecules, and the double bond is here on this double bond, and then another carbon you focus on here, another carbon you focus on here, and all the way to here with this parenthesis, that means you closing a ring. So basically here is closing the ring, so you pay attention to almost everything. And here you can see here is this carbon. So after you close the ring, then you go to the carbon B here. So you can see it really light up in carbon B. And when you output the oxygen, you kind of see it really light up on these two oxygen. So this is just one example. So that means our model do actually learn the spatial information of the molecules, of the images. So basically in this project, we build a model to translate between physical molecular models and their digital counterpart. Is there any questions?